Okay, so as we said at the end of the last segment, we want to find the mass if we have a density function rho of xy. Now rho would be like in kilograms per square meter, grams per square centimeter, grams per square whatever. And you have a function, so if you plug in the x and y coordinates of a point, you know at least at that point what the density is, and you expect then, if this is continuous and so forth, that in the near neighborhood of that point, the density doesn't change by a whole lot. Okay, we'll kind of hold that thought. So what we're going to do is we've partitioned the x-axis and we've got these strips. And we know that we could integrate these to get the area, but from one end of the strip to the other, this rho of xy function can vary like crazy. So we're not going to be able to do anything where we can really use this density function on a given strip. Well, what do? Well, we partition the ith interval. Partition the ith y interval, okay? The one I've got here. Okay, so again, the interval goes from negative square root of a squared minus xi star squared to a squared minus xi star squared. And the y values will go from there to there. So our partition is going to be, okay, well, let's see. Now, we could call it y naught up to ym. We don't want to use n because we're not going to assume that the number of intervals here is equal to the number of intervals here, although we probably could without too much loss for most functions. But we're going to use an m instead of an n for how many there are. How many points on the partition? Well, how many intervals there are. There are m plus 1 points, but m intervals. But we're going to keep the I because we want to know that what we're doing is we're partitioning the y values for the ith interval of the x partition, okay? Because we're going to want to do this for every interval of the x partition. We want to be able to distinguish the partition for the y interval for one x interval from the y interval for another x interval, okay? So here we have our partition, and what we then have is we have m of these in this one x partition, in this one interval of our x partition. We call each interval an x sub I, y sub j interval. So for every I and j, we have a y interval within the ith x, well, for a given I, then for any j, we have a subinterval in the ith strip, okay, corresponding to the ith subinterval of our x partition. And those intervals will be little squares, won't they? Okay, or little rectangles, they won't necessarily be square. Well, then, on each tiny rectangle, the area is going to be our delta x sub I times delta y sub ij. Okay, in other words, this width by the height of our y subinterval, our jth y subinterval. So our subinterval is going to maybe, this point then will be xi star yij star. Now, assuming that our delta xi and our delta yij, let's go ahead and label those and make sure we understand what they mean. Here's our delta xi. And that's going to be the same for every partition, every y partition, every y subinterval on our ith strip corresponding to the ith subinterval of our x partition. And here then we're going to have our delta yij, leave myself much room, but that's going to be this dimension. That's going to be the dimension of the jth subinterval of our xi strip. Okay, so we have this sample point in these dimensions. Now, we evaluate the density at this sample point. That gives us rho of xi star, yij star. And we multiply that by the area, which is delta xi multiplied by delta yij. So the mass within this interval is this. Total mass in the ith strip is the sum from j equals 1 to m of rho of xi star yij star times delta x sub I times delta y I sub j. Okay? Xi star being constant and delta xi being constant through this whole strip. Okay? The total mass, and it's approximately this, okay, total mass in the circle is the sum from I equals 1 to n of rho of xi star yij star delta xi delta yj. And I'm gonna make a little change here. Delta xi is the same, as I said, throughout this ith strip. So I'm going to write delta xi last, and you'll see how that makes things more convenient here in a minute. So we're going to have delta yij delta xi. Multiplication being commutative, we could write it in either order. But delta xi is constant for the ith strip. So for each of these n strips, for I equal 1 to n, xi will be constant. So we can write, we can write our expression with parentheses here. Okay? Meaning, and you know, I wrote things out a little prematurely. It's not quite correct, is it? And I probably want to reposition that parenthesis. Okay. This is the sum from I equals 1 to n, that's I, of the sum from j equals 1 to m of this expression. Okay? This can be summed up without having to worry about delta x sub I. For every I, we can do this sum without worrying about delta x sub I because it's the same for every interval. And then we can take whatever we get from this sum multiplied by delta xi for each I and add them up. And the other thing that we might just want to do is we might not want to use the same m for every strip. Remember, we got just a whole bunch of these strips. We got a strip here, one here, one here, one here, one here, maybe millions of them. So some of them we might, especially since some of them are going to be shorter than others, we might well choose to use different numbers, a different number of subintervals for different strips, meaning that our M here could be an M sub I, a different M for every I. Now don't let that distract you too much, but that could be a useful notational convenience that gives it a little more flexibility in how we set these approximations up, if we're doing an approximation. Okay, so it's a little more general if I use that, but if you don't understand why I did that, just, okay, they're all M, it's okay. In any case, this approaches the sum from I equals 1 to n of the integral from the square root of a squared minus xi squared to the square root of a squared minus xi squared. I think I said the negative here. From here to here. Okay, so the limits are going to be square root of a minus x, negative square root of a minus x squared to the square root of a minus x squared. And it's going to be rho of xi star y dy. Now put parentheses here, things are getting a little crowded. Then that's times delta xi. In other words, this expression here for each strip will approach an integral, just as happens in first year calculus. And then this sum from I equal 1 to n of delta xi, as your delta xi's get smaller and smaller, approaches an integral from, well, x goes from negative a to a. And that's then the integral of that the inner integral stays the same, except now our xi's merge into just an x, okay? And our integral with respect to x goes from negative a to a, because that's how we partitioned our original x interval from negative a to a, okay? Our original x interval was partitioned from negative a to a. So, there we have it. Now, I'm going to erase some of this stuff and write this stuff here out just a little bit bigger, so you can see in summary what's going on.